Okay, just a second. So today's lecture is on mapping. Mapping is another fundamental problem in robotics. Meanwhile, can you hear me properly? Can you just type in chat if you can hear me? Thanks. So mapping is another fundamental problem in robotics. One fundamental problem we already discussed is localization. Mapping is tightly coupled with localization. That is why sometimes people solve both of these problems simultaneously. We already discussed shortly that there are so-called simultaneous localization and mapping algorithms, which are quite popular nowadays. We will not discuss these types of algorithms in this course, but we will separately discuss localization and mapping, and to do it simultaneously, it's just a matter of combining those approaches we are discussing. So today we're going to talk on mapping problem definition. As usually, we will first define the problem we are discussing. Then we will discuss which types of maps are applied in robotics. And there are topological features or landmarks maps and occupancy grid maps. We will discuss all of them separately. So just as a reminder, we are still working inside this scheme. This is a control scheme of modern mobile robots, simplified one. And as you remember, we already discussed sensors and we discussed localization. And inside localization, we also discussed motion and observation models. Motion models are something which describes our motion with noise, and observation models are models which describe our measurements, which also subjected to noise. And inside the localization, if you remember, we always said that there is some map of the environment which we use to compare what we see with this map to make a decision how good our hypothesis on our pose, how probable it is. So today we are discussing how these maps are obtained, how they constructed in robotics. And also you can see that in further lectures in path planning, for example, we also will use maps. So it is important for us to understand what are maps and how they are built and how maps are stored and represented in robotics. So mapping in robotics refers to the process of modeling the environment and representing it in a form that is convenient for further use in navigation. We mostly use maps in navigation, and by navigation we usually mean the combination of localization, planning, and motion implementation. So everything to get from point A to point B is called navigation, and it includes our ego pose estimation, so localization, then planning of our motions and implementing those motions. And why mapping problem is difficult? Because, as we already know, sensor measurements are prone to errors. Our measurements generate incomplete or inconsistent data sometimes. So two measurements can be in conflict even though we made them with a single sensor. Also, we know that ego position or localization are prone to errors, and we know already that we never can be 100% sure where we are. But to perform mapping, we have to know where we are, because mapping is something, putting something on the map means that we know where we have to draw it on a map. So we know where we are, we know where we perform a measurement. Also, there is a problem how to integrate data over time. Imagine we have thousands of measurements with our lidar or camera or something, and these measurements are performed in a time interval, right? And within this time interval, something can change, and we have to integrate it over time somehow. And also, there is a separate small problem in mapping, which is called loop closing. And this problem is about understanding that we already visited the same place. So we have to come up with a mechanism to say that we already have been in this place and we already have seen what we see right now with our sensors. It allows us to decrease an error, because error can be drifting in time, and loop closing or understanding that we already visited some place allow us to minimize or cross out the error which is summed up over time. So formal mapping problem definition is the following. Given all poses of a robot over time or states of a system, and all sensors measurements, we can have single or multiple sensors, but we have the whole history of our sensors measurements. We have to find a map. And by map, we mean some representation of the environment. And here on the slide, you can see the representation of a robot map. We will discuss. This one is called occupancy grid map. We will discuss it further in the lecture. But we have to build something like this for our robot, having all poses, given all poses. So we are not already solving localization problem here. We think that we are given these correct poses of the robot, and also all sensor measurements. So there are two dominating types of maps used in robotics. There are many, many more. You have to know that there are more than those two groups, but they're more exotic and used quite rarely than those two. So we will discuss this, the most popular maps, and majority of scientific works you could read on robotics will use either of these two types of map. So metric maps is something which is reflect the world in a form of 2D or 3D space, depending on how we navigate. For example, as we know already for our wheeled robots, we usually use 2D representation because we think or we assume that the floor is flat, and we don't have to use altitude to navigate our robot. But for for example, flying robot or drone, of course, we have to use 3D representation because we have altitude, which we also have to control, and we have to know where obstacles on which height there are obstacles. So 2D or 3D space. In metric maps, objects are set by their coordinates, like real coordinates in meters or centimeters or something. And distance between objects is measured in meters, as we already said. And there is another type of maps, topological one. This type reflects the world in the form of places or locations and connections, transitions between them. So we kind of have a graph, and usually topological maps are represented by graph, where we have places and some connections between them. Imagine your room or your flat. You have kitchen as a place or location, and you have bathroom as a place or location, and then you have some transition, which is some law which allows you to follow from your kitchen to your bathroom or something like this. And distances between objects can be stored in links. So within these links between locations, we can store either distances or any additional type of information. For example, explicitly within these transitions or connections, we can store control law, which allow us to control our robot to move from one location to another. So this is also very rich representation of the environment, which can be modified for different tasks. So examples of maps, like you all know metric maps. Our classical world map is metric. We have longitude and latitude there to measure distances, or any 2D map in meters is also a representation of a metric map. And there is also example of 3D map built from point clouds. You remember that point clouds is something which is generated by, for example, LiDAR. And there is a 3D representation of the environment. You can see houses there, roads, and all distances are proportional. They're proportional to real world with some scaling coefficient. So we can say that all these distances in this map are measured in meters. And topological map, you also know, you all have used metro or subway. And this is the really good representation of topological map. We have some places or stations, and they're connected with links or connections. And this is the type of topological map. So you know that to travel from one station to another, you have to follow the particular road, right? And this map gives you this information. And this is a simple example of flat or apartment represented by a graph, also by a topological map. You can see that every room is a node inside the graph, and path between rooms is an edge in this graph. Yeah, and these maps, oh, I'm sorry for Russian here. So these maps are usually metric maps are represented either by occupancy grid maps, which we will discuss further, or by feature-based or landmark-based maps. And also they sometimes have semantic component. For example, here you can see that different rooms colored with different colors. This is still metric map, but we have an additional information, or our robot has an additional information, that this room is office and this room is a kitchen and this is a corridor. So this is some additional semantic information which is sometimes added to robotics maps for some reason. For example, we can have different control laws for different rooms because we know that there is carpet in office and there is like some sleeping surface in corridor, something like this. So this information can be additional, which we can use in controlling our robot. And regarding topological maps, they, as we already said, usually represented by graph, and there are links between nodes in the graph, and nodes are usually some recognizable places. So let's talk a bit more on topological maps. We will not discuss them in details because they're still rarely used in robotics. Like metric maps are the most popular type of maps used. And topological maps are not that popular, but still sometimes used. Let's discuss a little bit more. So as we already said, there are locations, which are nodes in our graph, and transitions between them, which are edges. Locations are usually places in which robot can be reliably positioned or localized. For example, we can be sure that we're inside kitchen and we can precisely tell our location inside this kitchen. Then we can say that kitchen can be a location, recognizable one, so we can recognize or distinguish kitchen from a corridor. And then inside these locations, our robot usually makes a decision where to go further and how to go. Yeah, and transitions are just passes between these locations, which again, as we said, can contain the control law, how to travel from kitchen to, I don't know, a living room, right? We know that there is a door in kitchen and we have to follow through this door with not really high speed, and we have to check that door is open beforehand to travel from kitchen to living room. And such laws, control laws, can be directly encoded in these transitions between our locations. And you can see that there are many algorithms how to split our environment within this graph. And there is Voronoi diagrams. This is a type of diagram which is constructing some passes which are on the highest distances from obstacles, and Voronoi graph is a good algorithm to split our environment into locations and to build transitions between them. We also can just manually choose topological regions, and from any of this representation, in the end we get topological graph where nodes and transitions between these nodes are edges. So main drawback of such a representation is that topological representation is really, really difficult to obtain for some large open spaces. Imagine a desert. There are no features, no recognizable locations, and we cannot build such a representation because we just don't have a rational way to split the environment into regions, into locations which would be recognizable, right? So for open space, for outdoor navigation, sometimes it's really difficult to use topological maps. And this is their main drawback. The second type of maps is a feature or a landmark map. Such type of map stores features specified by their coordinates in space. That is why it is still a metric type of map, because features are specified by their coordinates. And by feature or landmark, we can mean anything, right? Anything which we can detect or recognize. For example, if we have a computer vision algorithm which can recognize trees, trees can be our landmark. So we can detect trees distinguish them somehow. So we can say that tree number 1 is different from tree number 2, and we can reliably recognize one from another. So trees can be our landmark. We can use road signs, doors. We can use some features which are image key points, something artificially built, not some object from a real world, but some artificial features we can construct on image or point cloud. We can use this. The main criteria is that we can detect it and distinguish one from another. And if both criteria are satisfied, we can use this object or this notion as a feature or landmark. And such maps have very compact space representation because we can have just a vector of these features and landmarks specified by their coordinates, and detecting new feature, we can just run through this vector and compare if we have seen something similar already, and we can understand either we see this location or those locations. As we already said, this difference between feature and landmark is that landmarks is usually something natural or man-made, some object, right? For example, tree or road sign. And feature is something usually artificially built up and usually more abstract. For example, here on the slide, you can see example of image features, so-called key points. Those are points which are recognizable on image and distinguishable from other image regions. For example, it can be some corner of window which can be recognized on different on images taken from different viewpoints or with different lighting conditions. We can still recognize this corner, and this is a good feature. This is not something like a tree, right, or a road sign. This is just a corner, some image intensity change on image, something really artificial, but we can recognize it somehow, and we can then describe. For example, there is a popular description or key point descriptor called SIFT. What we do here, we just build image gradients around the key point, and then we have some key point descriptor, which is just vector of these gradients. And we say that we described our key point, and then we can compare these descriptions of two key points, and we can make a decision either we see the same key point or different one. For example, for this one and for this one, these descriptions will be very different, and we can tell that those are different key points. And this allows us to, again, describe the environment, to store it in some map, in some compact representation, and then seeing some picture, we can compare it with our representation, with our map, and we can say either we see one location or another. So these are feature or landmarks maps. And they're usually built with Kalman filter. If you remember, in Kalman filter implementation we discussed, we were estimating our own position, right? We were estimating the pose of the robot. And for that, we had our motion model, and we had our measurement. We compared them and made some decision on how precise our pose is using two Gaussian distributions, one from measurement, one from our prediction. But Kalman filter, as we discussed, can be used for any state estimation problem. And building features or landmarks maps is also state estimation problem. We have our poses in this case, so we are not estimating the robot pose because we are given all poses of the robot and we believe they are quite precise. But what we want to estimate pose of the landmark now. And for that, we also can use Kalman filter. We just have to rewrite some matrices there. And each feature or landmark is encoded with its own position, the same as our robot was encoded with its position. And to estimate landmarks, we iteratively refine their position with each new measurement. So we have a detector which can detect the position of a landmark. And then using Kalman filter, we try to estimate this position more and more precise with new measurements. So imagine we have a first measurement. This is a Gaussian distribution with mean somewhere here. And this is not quite precise measurement of the pose of our feature. And then we have a second measurement. In combining them, you remember that we multiply these Gaussian distributions. We obtain something more precise, and this is a resulting landmark position. If with more and more measurements, this position estimation will be more and more precise. And we do that for any feature or any landmark we detect, which could be hundreds or thousands of landmarks. We use a huge Kalman filter where there is a kind of small Kalman filter for each feature pose estimation. And in the end, we get the positions of every landmark we detected, and we construct a map from it. So this is how Kalman filter used to build a map, not to localize a robot. So, and the last type of maps we will discuss today, and we will spend more time on this because, as we said, this is the most popular representation of maps, is occupancy grid map. This is the most popular maps format. Space is discretized into cells in these types of maps, and usually we use a regular grid to discretize our world, but this is not always the case. You can use different types of grids, and each cell of such a grid is either free, passable, or occupied impassable for our robot. So here is a simple example of occupancy grid map. It's already binarized, so there are just two colors. White is something where a robot can go, and black is something where our robot cannot go. In the middle representation of occupancy grid map, we actually can have probabilities. So in each pixel of this map, or in each cell, we'll have the number from 0 to 1, for example, which will say how probable that this cell is occupied. So we will see it in a couple of slides, but for this slide, this is the types of our space discretization. We said that usually we use regular cell decomposition, but sometimes we can use more exotic types of space splitting. For example, we can use quad tree, which allow us to have more precision around obstacles, because we want to know more precisely how to travel around obstacles, and we will have less precision in regions which are huge and which are basically free. We can also use more simple rectangular cell decomposition. Even though if our obstacle has a complex shape, we will still have a wrapping rectangle here, just to simplify our computations, because comparing these two, you can see that here we have less numbers of cells, and of course the less cells we have, the simpler our computations will be. And there are more and more types of these cells decompositions, but you have to know that usually we use regular cell decomposition. So it is the same as image. We split our image into similar squares, which called pixels, and this map is basically an image, right, where each pixel store probability of this cell being passable or impassable. So talking more on map representation, each cell can be represented by a binary random variable, because each cell contains number which tells us either there is obstacle or not. And if if number stored in a cell is equal 1, we consider space to be free. So white squares are free. If cell stores 0, we consider cell to be occupied. Black cells are occupied. And if cell contains 0.5 probability, we cannot say anything about this cell. So the cell is grayish, and we cannot say anything, right? Because probability 0.5 tells us that there can be obstacle, or this cell can be free with equal probability. And there is the whole spectrum of numbers between those. So we can choose the threshold. For example, if we have probability in a cell 0.7, we can either consider it to be free or occupied depending on us. So we choose a threshold, and from this representation where there are gray cells, we can in any time get this representation where we only have two colors, just choosing threshold. For example, anything above 0.7 is free, and anything below 0.7 is occupied. And we can choose this number. So there are several main assumptions we make while performing occupancy grid mapping. And it is important to understand these assumptions because all of them are quite severe. And there are many algorithms which try to fight these assumptions. So we are discussing just a basic type of occupancy grid mappings, but of course there are people working on this topic yearly, and there are many algorithms which try to overcome these assumptions. But still, in a basic form, there are many assumptions we make. So saying that cell is occupied or cell is free, we mean that the whole cell is occupied and the whole cell is free. It is important because this cell, depending on our scale, on scale of our map, it can be either 1 centimeter by 1 centimeter, and then it is not really crucial that the whole cell is considered to be occupied or free. Or we can choose a scale where this square is 1 meter by 1 meter. And this is important then because if there is a person, in reality, the person occupies only a small portion of this cell, right? But we will still say that the whole cell is occupied or the whole cell is free. So we kind of choose which precision we will have by choosing our scale. But of course, with the higher scales, we have to put more computational resources to work with this map, and that is why this is trade-off on scaling, and we make this assumption that the whole cell has a single state. Then we think that the world is static because we don't have an option to rebuild map every second. Of course we can, and sometimes robots do that. They really rebuild this map all the time. But usually we build this map once, and we have to make this assumption that the world is static. And then if we say that the cell is occupied, we mean that it's always occupied. So of course we have procedures sometimes to rerun mapping just to check if something changed. And real robots do that. They, for example, the vacuum cleaner robot, it rebuilds map periodically, right? But at the moment of building the map, we say that the world is static and everything we see is static. And the third assumption is that cells are independent, which also not always the case. For example, if we say that this cell is occupied, of course, there is a high probability that neighboring cells are occupied, right? Because we can, for example, if we see the wall, of course, we know that if this part of the wall occupied, the neighboring parts are also most probably occupied because it is a wall. But here in our simple mapping, occupancy grid mapping, we say that each cell is independent random variable. So here we said that each cell is a binary random variable. It is important that it's independent binary random variable. So these three are the main assumptions we made. Of course, you can argue all of them, and not all of them are not true in real world, but still to simplify things and to allow us to come up with a simple mapping algorithms, we have to use these assumptions. And then the map representation, the probability of a map is given by the product of independent probabilities of all cells. So to compute the probability of particular map, we just compute the product of each cell. And here is example. If we have a map like this, the probability of this map will be equal to product of probabilities stored in each individual cell. And probability of the map we want to compute because in some algorithms, in some mapping algorithms, we just compare several maps and see which one is more probable, given our measurements, of course. So to compute the probability of a map, we just we just compute product of each individual cell. And as usual, we will discuss probabilistic mapping problem definition. We already discussed classical one. Classical problem statement, and here is a probabilistic one. Given the vector of all consecutive sensor measurements, Z, and robot poses, or in this case, actually, for us, it is important not a robot pose itself, but a sensor pose itself, but which we use for mapping X, we need to build or recover the most probable map. And the most probable map, given given our measurements and our poses, is a product of each individual cell, given our sensor measurements and poses. So this is a probabilistic mapping problem definition. And we will discuss several algorithms which allow us to solve this problem. The same as we discussed in localization, that there is Kalman filter, there is particle filter, and many more. There are also several types of algorithms used to build maps, occupancy grid maps. And the first and the simplest type of algorithm which you can come up on your own, it is really simple. It is called hit-miss mapping algorithm or mapping algorithm with counting model. And here the idea is really basic. We can remember that probability is actually can be treated as frequency, right? So probability of some event, it is a frequency of, for example, successful outcomes of this event divided by all trials, right? So this is a frequency-based probability definition. And in this algorithm, we do the same. We just compute a number, C, how many times have we observed a cell, particular cell with coordinates X and Y. So we have our map, each cell has a coordinate X and Y, and you have seen it already in this slide. And we compute how many times we observed particular cell, each cell actually. So we store this number for each cell. And also we have the second number, O, which we will either increase or decrease by 1 each time we observe an obstacle or free zone in this cell. So we have our sensor, for example, LiDAR, which tells us where obstacles are and where free space is, right? And each time we see an obstacle in particular cell, we will increase this value O for this cell. And each time we see a free space, we will decrease it by 1. And in the end, we just calculate the probability given this formula. So it's quite simple. It is all about frequency, how many times we have seen obstacle in this particular cell. And this will get us, will give us probability of obstacle being in this cell. And this is quite simple. This algorithm really works. It doesn't work in complex environment, but still it's quite straightforward. It's really computationally official because everything we have to compute is just 2 numbers. So you can use these simple algorithms. The second type of algorithm, it is well known for us already, Bayesian estimation. You remember we had something really familiar, really similar in our localization lecture. So what we want to estimate is probability of cell being occupied. This M means that cell is occupied, given our measurements and given our poses. So we can again use Bayes rule, and from this get this equation. You can see that here z to time t minus 1 already, because that on time t is here. So this is just simple Bayesian equation. I hope you remember it still. So we get something like this, then we use Markov property, and you remember that Markov property tells us that the state of the system now defines the future, and the future doesn't depend from the past if we know the current time, current state. So here you can see that, of course, map cannot depend on x on time t, because that is why we use t minus 1 here. So we drop the last pose basically. And the same here. So first of all, we know that measurement in current moment of time doesn't depend on previous measurements, which is logical. Sensor readings or sensor measurements are considered to be independent. So the current measurement doesn't depend on previous ones. That's why we drop this vector z. And also, we know that current measurement depends only on current pose, right? So where we are right now defines what we will measure, and our previous poses doesn't influence what we measure right now. That's why we drop all the vector of poses and we are left only with pose, with the current pose using Markov property. Then we again use bias rule here, and we know that map is independent on pose here, which is called independence property. So our value of probability of the cell of map doesn't depend on pose. Of course, map exists without our robot. Doesn't matter where our robot is. Map still has some probability. So when we come up with something like this, with some huge equation, which looks really scary, but we can perform the same for an opposite event. Just notice here, this probability is probability of map being occupied, and the opposite event is map of being free. And we can come up with the same exactly equation for opposite event of map cell being free. And we get the same huge equation, but in all places our map cell event is opposite. And we can calculate a ratio of those two probabilities, of those two events. So here in the numerator, the probability of map cell being free, being occupied, and in denominator, the probability of map being free. We have these two huge equations, which are quite similar. We can cross out some members, and we are left with something like this, which is still looking really huge and scary, but we'll analyze what we get here. And again, for an exam, you don't have to remember these huge equations and how to derive them. You just have to remember the final one, which is quite simple to understand. Let's see. So there are three members, product of three fractions. Let's see what each of them means. The first one, we can see that there is actually probability of map cell being occupied given current measurement and current pose. And in denominator, the same event, but the opposite, 1 minus this. So this is basically the probability of map being free for the current measurement and current pose. And this is the ratio of probabilities of cell occupancy and freedom under the condition of new measurement. So we obtained a new measurement and we see how probable that map cell is occupied or it is free in denominator. And we have ratio of those two things. The second member, you can notice that this is exactly the same, but for the previous moment of time. So this is a recursive member because we will have in every algorithm step, we will have recursive members. So for previous time stamp or time moment. But those two are the same. You can notice that, right? And the third member is ratio of prior probabilities. So probabilities of map not depending on measurements or robot poses. So this is a prior probability of map being free or occupied. And this one we can choose. So imagine we know nothing on a map in the beginning, right? So we just switched on our robot in some unfamiliar place, and robot doesn't know anything on map. So it is logical to assume each cell to be to have a probability 0.5, which means we know nothing. Each cell is either occupied or free with the same probability. That's 0.5 probability. But we can choose any number here because this is our prior. We have to somehow estimate our prior probability. For example, if we know that we're, I don't know, on a road, right? We're a car driving on a road. We know that the probability that space is free is higher than the probability that there is an obstacle. That's why we can, as a prior probability, use some other number, which tells that the probability of cell being free higher than probability of a cell to be occupied. So remember this equation. We will come back to this equation in a moment, but for now we just have to discuss something abstract, some notion from mathematics, which is called odds and logarithmic odds. So odds is a is the probability of some event. So odds of event X is the probability of X divided by the probability of an opposite event. So in the numerator, we have probability of X, and denominator 1 minus probability of X. This is called odds or chances. Sometimes in Russian, we call it chances. So this is the notion showing how probable this event. So what are odds? You can see this phrase sometimes in casino or some game. What are odds of event X? And logarithmic odds is a simple notion. We just take a logarithm of both sides. So logarithm of this fraction, this is called logarithmic odds. And here you can see something really similar to this, right? So probability of event divided by probability of 1 minus this event. This is exactly what we have here. And here we have just turned out the same odds. So we can use this mathematical thing, mathematical notion to somehow to perform something with our equation to make it simpler. And let's see. So this is odds, and this is 1 divided by odds, basically. And if we calculate logarithmic odds from each part of this equation, we will get something. So here are log odds of event of cell being occupied, right? So we can, in denominator here, we can write 1 minus this event, because we have an opposite event here. And since it's a binary random variable, so cell either occupied or free, that is why 1 minus probability of cell being occupied, this is exactly probability of cell being free. That is why here we can get this log odds. And then we will also have log odds of these 3 components. And you remember that product, if we take logarithm from product, we have to substitute multiplication by summation. And since here we have 1 divided by logarithm, we will get minus here, not plus, but minus. Between those two, we will get plus because these are pure logs, log odds. And here we get minus because this is 1 divided by log odds. And we'll get such an equation, which is quite simple. This is just, so log odds of a map being occupied, given all our sensor readings and all our poses, this is what we are looking for, is equal to sum, or like summation, let's see, of three terms. It is really simple. It looks much simpler than this crazy formula with fractions and multiplications. And you can see that here is the probability of a map being occupied given the last measurement. Here is our recursive term, so the previous probability of a map given previous measurements and previous poses. And here is our prior, so we substitute our prior every time. And we will use this formula to build our map. And this one you have to know is called inverse measurement or observation model. You remember we already discussed measurement and observation models, and this one is called inverse. Why? Because in our measurement models, we were estimating probability of measurement of Z given map and given pose. Remember, in Kalman filter and particle filter, we had the same thing, but we were estimating the probability of Z given map and given X. And here is vice versa. We're estimating the probability of a map given our measurement. And this is called inverse measurement model. And this is also called inverse because it's quite unlogical. Look, we are saying that the map depends on the measurement, but we understand that in real life, in real world, it is vice versa. Measurement depends on the map because map is something that is already exists even without our robot. And what we measure with our sensor or with our robot depends on the map, right? But here we say something contradictory. We say that our map depends on our measurement. And this is also why it's called inverse. And here is occupancy grid mapping algorithm. This is pseudocode, which you really can implement in like 8 lines of code. It's quite simple, but it is really efficient because in reality, it uses all power of Bayesian estimation. So we really derived this thing from these huge equations. And in code, it looks so simple. That is why this is the most popular algorithm, because it is really simple to implement, to program, but it is really powerful, and it uses all power of Bayesian estimation. So let's see. As an input of our algorithm, we get the previous map state. So L t minus 1, this is, you can see our previous map state. So this is our recursive member. So the previous estimation for each cell. We also get as an input in this function current state and current measurement. So imagine you have a robot which is driving through the space. It has its own pose and it has measurements. And each time we get new measurement and new pose, we will call this function, occupancy grid mapping function. And then once we have this new measurement and we called this function, for each cell of a map, if this cell in perceptual field of our measurement, of course, we don't want to spend much more computational resources to running through all cells of the map, right? Because map can be huge. So we can have many of these cells. Of course, we don't want to update cells which are not in field of view of our robot. So imagine this measurement, Z. It's our LiDAR measurement, and we know that our LiDAR measurement cannot measure like every cell in the space, right? Because there are obstacles we cannot measure behind them. That is why there is additional check. Do we even have to update the map cell given our measurement? Or maybe for some map cells, we can just skip this step and just to make things faster and more computationally efficient. So if the cell is inside our perceptual field, so we have some information for this cell in our new measurement, we just perform this update. This is exactly this equation. So we have our previous state of the cell. We compute so-called inverse sensor model, this one, and we will discuss in a minute what can it be, how this inverse sensor model can be constructed. And we substitute our prior each time. But interesting thing is the following. You remember that we said that if we know nothing on our environment, we can use our prior equals 0.5, right? Which means the probability is that this cell is occupied and probability is that it is free. In the beginning, we just don't know. That is why these probabilities are equal. So try to put 0.5 here, right? What we will get? We will get 0.5 in the numerator and 0.5 in denominator. And the whole thing will be equal to 1. And logarithm of 1 is 0. And that is why we can cross out this term, and we cannot use it in our equation. And equation will be even simpler without this minus every time. But this is only the case if we know nothing in the beginning. If we know at least something, for example, we know that we are in a desert and the probability that space is free is much higher than the probability that space is occupied, it is convenient for us and logical for us to use this additional information to make our map more precise, and then we will have this term. But if we know nothing, we can cross out this. So for each cell, we make this simple update. We just have something in the previous time moment, and we sum it up with our new information computed through inverse sensor model. And that's it. This is our new estimation for map cell. And of course, in the end, we can just take exponent from this and compute just the probability, right? Because we actually not computing probabilities within this function. We're computing log odds, logarithmic odds. But we can easily, from logarithmic odds, if we know that we finished mapping our environment, we just compute for each cell, take exponent and compute p of x, and we get a probability. But for us, it's just much more convenient to use logarithms, because here we have a plus instead of product. And you all know, I guess, that plus or summing is much more computationally efficient than multiplication. in any programming language. So that is why we want to use summation instead of multiplication. And let's see how this measurement model. So we said that there is some inverse sensor model, which is unfamiliar for us. Let's see how it can be constructed in real life for real sensor. Imagine we have a sonar. You remember that the sonar is some sensor which uses ultrasound to check if there are obstacles. You all remember that sonar has something called field of view. So we check obstacles within some field of view, which is shown by black lines here. And this is our robot. This is black lines is the field of view of our single measurement. And you also remember that sonar emits ultrasound, measures time it takes for ultrasound to travel to obstacle and come back. And by measuring this time and knowing the speed of flight of our ultrasound wave, we can compute the distance to our obstacle. And also important feature of sonar you have to remember and have to know to understand this model is that by computing distance to obstacle, we cannot say where is this obstacle exactly within our field of view. So imagine our obstacles, they're colored in black here. We measured some distance along this red line equal to some, let's say 10 meters. And we don't know where within this beam this obstacle is, because and that is why we consider all cells which are on a distance of 10 meters, on a measured distance. We consider all the cells being occupied. And this is shown on this picture. So all cells within our field of view, which are closer to us than measured distance, are colored in white, which is mean we measured that they're free. And all cells on a distance which we measured are colored in black, which means our measurement have shown that these cells are occupied. And we cannot say which one of those. We know that is why we have to color all of them in black, saying that all of them are potentially occupied. So this is a single measurement of a sonar. And within this beam, we have different probabilities, right? So if we know that we measured the distance z, we can say that there are different probabilities for cells closer than z and further than z. For example, we know that behind the obstacle here, where cells are gray, the probability is equal to prior. So we didn't get any new information behind this measurement, right? Because we know that there is obstacle on some distance, but we don't know from a single measurement what is behind. That is why on this plot, there is a prior probability. We didn't measure anything. We know that closer than our measurement, the probability of cells of being free is higher than being occupied. This is shown in white. So we kind of measured that this space is free with our single measurement. And everything around our measured distance can have like some different shape, different probabilities, but the main idea is the following. Something close to our measured distance is called occupied, because we measured that there is something on this distance. And this is a typical simple sonar measurement model. And basically here, with this inverse sensor model, what we will do is that iterating over the cells on a map for cells which are within our perceptual field of view, for cells which are closer than measured distance, we will write some probability of being free to them. So we will have initial probability and we will add some probability of being free. And for cells which are further away, which are on a measured distance, we will add some probability of being occupied according to this function, which we came up in the beginning. We said that our sonar measurement model is something like this. We've got it from experiments, and you remember how we constructed the quite similar model for our LiDAR in the previous lectures. So this is a quite simple measurement model which models the measurement of our sonar, and we can use it here to just add some probabilities to cells either being free or occupied. But there is some problem with our simple occupancy grid mapping algorithms. This form of algorithms is called occupancy mapping with inverse sensor model. But there is also algorithms with direct sensor model, so occupancy mapping with forward or direct sensor model. And what is so bad about inverse mapping? So our model or inverse model considers cells of a map being independent random variables. You remember we said it several times that our cells are considered to be independent. And this is a problem because sometimes we have a contradicting data which cannot be explained with this model. Let's see an example. Imagine we have our robot moving, we have a sonar on the side, and you can see two consecutive measurements of a sonar. And first measurement says that we have an obstacle on some distance. You can see that there is a really real obstacle. And since we don't know where is this obstacle within our field of view, we discussed it already, we have to draw obstacles all over our field of view on a measured distance. Even though in reality, you can see that we detected only the corner of an obstacle, we will draw the whole line here because we don't know in our sonar beam where this obstacle is. And then we have a second measurement, and we also see some obstacle, or in this case, we actually don't see an obstacle, but we have a maximum measurement. You remember that sensors, when they don't see an obstacle, they give some maximum number, and it is sometimes difficult to distinguish either it is no obstacle or it is an obstacle on a maximum distance. So in this case, we decided that there is obstacle, but for us important is this thing. So second measurement didn't measure any obstacle in the beginning, and it is correct because you can see that there is no obstacle in our field of view. But first measurement had some obstacle in the middle because we draw this line because we didn't know where obstacle is. And we've got some contradicting data here. We have some conflict because our two measurements are conflicting. And it is for this type of algorithms with the inverse sensor model, it is quite difficult to demonstrate why, but you have to know that for this type of algorithm, most probably we will have some probability of obstacle here. And that is why our map will be not really correct in this place, can be not really correct. It is not always the case, but sometimes we can have such conflicts, and that is why our map can be not really correct in such complex environment. That is why people came up with other types of algorithms. We will not discuss them in details, but the idea is quite simple. There is so-called mapping with direct or forward model, and we do the opposite thing. Here, we said that each cell is independent variable, and we were trying to compute the probability of each independent cell, and in the end, we have a binarization threshold, and we were getting our map like this. So using binarization, we just binarized our map, and each cell was considered either occupied or free, but independently. In the forward mapping, we use another idea. We are searching for the entire map, and we consider mapping as an optimization problem in the space of all possible maps. So imagine we have let's see an example. Imagine we're estimating the map, which is 2 by 2, really a small environment, really simple map. We're considering all possible types of maps here, and you can understand this is 2 to the power of the number of cells, right? So there are many combination. So 2 to the power of 4 in this case combinations of this map, and we are trying to modify this map and to find the most probable map within all possible maps here. So in the simplest case, we can just randomly change all cells, like one by one, compute this probability of a map, and see which map from all possible combinations is the most probable one. Of course, for big maps, for real maps, we can't consider every combination, because there are exponentially huge number of possible maps, right? That is why we have to come up with some smart optimization algorithms to somehow see which map is the most probable from all possible maps, but not to spend the whole life to trying to compare different combinations. So the idea of mapping with a forward or direct model is to consider mapping as an optimization problem in space of all maps. And you can see here that we're using arg, we are trying to find arg maximum in the space of maps given probability of measurements. So for each possible map, no, not for each, but for different possible maps, we are seeing what the probability of measurements given the map, and making a decision that the map is correct or not correct. I hope it's quite understandable. If not, ask questions here, because this is quite a complex approach. But the main idea here is that we say that all maps are possible, and trying to use some optimization technique to find the most probable map. And by the most probable map, we mean that the map is explaining our measurements in the best possible case. So there are many approaches which are realizing this optimization. We can use gradient descent or expectation maximization algorithms. We will not discuss it in this lecture, but for now I want you to understand that mapping can be treated as optimization problem. And you can actually take something like this for your term project, and it would be really great if somebody will get into details of this mapping with a direct or forward model, and will build on some public data set, which I can suggest you the map using this direct mapping algorithms. So basically that's it for today. As usual, there are some additional resources on topological mapping, really cool lectures on robot mapping. There is a great article from Sebastian Trun, Learning Occupancy Grids with Forward Models, on this algorithm. And of course, there is always Probabilistic Robotics book, which is the most important book in this course. And there is chapter 9 you can read to find more on mapping. But I hope that you've got the main points, that mapping is also probabilistic because we have measurement noises. There are three approaches to build maps: topological maps, feature landmark maps, and occupancy grid maps. Occupancy grid maps is the most popular technique, and there are many algorithms to get this type of maps. The most important ones are mapping with inverse measurement model and mapping with forward measurement model. So that's kind of it for this lecture. There are several important things I said in the beginning of the lecture. First of all, there is first home assignment. It is already released. You can